Part 2, but can't I just control what I eat? 5. The 3 Ages of Eating. 3 Ages of Eating. The author proposes that eating can be divided into 3 distinct ages. Age 1. Geophagia. Eating non-living matter organisms consume non-living matter like rocks and metal for energy. This began with early life forms and continues today with certain bacteria. Age 2. Biophagia. Eating living matter organisms consume other living organisms or their byproducts. This started hundreds of millions of years ago and is the dominant form of eating for most species, including humans. Age 3. Ultra-processed food UPF. Consumption. A single species, humans, and their domesticated animals consume industrially produced food with novel molecules. This age is only a few decades old. Early Earth. The first 700 million years were characterized by asteroid bombardment. Despite this, evidence suggests the presence of liquid water and a less hostile atmosphere than previously thought. Early atmosphere was primarily composed of volcanic gases like carbon dioxide, nitrogen, and sulfur dioxide with little oxygen. Emergence of life. Evidence suggests single-celled organisms emerged around 3.5 billion years ago. By 3.2 billion years ago, life was altering Earth's geology, creating large iron deposits as waste products. Age 1 of Eating. Early bacteria consumed dissolved iron from underwater volcanoes, using carbon dioxide and releasing rust as a byproduct. This process is explained through the concept of atoms and electron transfer for energy production. Life as energy transfer. All life forms, from bacteria to humans, obtain energy by transferring electrons from food to oxygen or other electron acceptors. This process occurs in mitochondria, where electrons are passed along a chain of proteins, generating energy for cellular functions. Transition to Age 2. As competition for resources like iron increased, organisms evolved to consume other life forms or their waste products, marking the beginning of the second age of eating. Evidence of Age 2. Dickinsonia caustata, a flat oval creature, is considered the first recorded evidence of Age 2, as it left trails in microbial mud, indicating feeding behavior. This highlights the concept of ecosystems, where organisms eat, are eaten, and modify their environment. Evolution of Eating. The second age of eating drove the evolution of single-celled organisms to multicellular organisms, eventually leading to humans. Eating evolved to serve 2 purposes: providing energy and supplying building materials for the body. Essential nutrients. Living matter is primarily composed of oxygen, carbon, hydrogen, and nitrogen. Humans require about 20 additional elements obtained through diet for various bodily functions. These include calcium, phosphorus, sulfur, potassium, sodium, chlorine, magnesium, iron, fluorine, zinc, strontium, iodine, copper, manganese, molybdenum, and cobalt. Both deficiency and excess of these elements can be harmful. Herbivore challenges. Herbivores face the challenge of obtaining necessary nutrients while avoiding plant toxins. They achieve this through sophisticated detoxification mechanisms, learned behaviors, and diverse diets. Cow's diet. Cows consume a variety of plants, each with different nutritional and toxicological properties. They learn to balance energy intake with toxin load and identify beneficial plant combinations. This knowledge is acquired through experience and passed down through generations. The microbiome. Cows, like humans, rely on a microbiome, trillions of microorganisms in the gut, to digest plant fiber. These microorganisms break down indigestible components, producing short-chain fatty acids that provide energy and building blocks for the cow. Human evolution and cooking. Humans are unique in their reliance on cooking and processing food. Cooking increases the availability of energy from food, as demonstrated in experiments with pythons. Humans are considered cuisinivores, obligate cooks, and processivores due to their need to process food. Impact of processing. Food processing, including grinding, fermenting, and drying, has shaped human evolution. This is evident in our smaller teeth, jaws, and guts, as well as our genetic adaptations for digesting processed foods. Transition to age 3. While it's possible to maintain a second-age diet by consuming unprocessed foods, most people in the UK and US have transitioned to the third age of eating. This age is characterized by the consumption of ultra-processed foods containing novel, synthetic molecules not found in nature. The dawn of artificial sweeteners. In 1879, Konstantin Fahlberg, a chemist at Johns Hopkins University, accidentally discovered saccharin, the first artificial sweetener. He was working with coal tar derivatives and noticed a sweet taste on his hands and napkin after leaving the lab without washing them. Saccharin is 300 times sweeter than sugar and became widely used, especially during sugar shortages in World War I. Rise of synthetic food chemistry. The discovery of saccharin coincided with a growing field of synthetic food chemistry. Modifying starches and other carbohydrates was a major focus of research in the 19th century. Over time, thousands of new molecules were introduced into the human diet. Consumption of food additives. In industrialized countries, people consume an average of 8 kilograms of food additives per year. This amount surpasses the consumption of basic ingredients like flour, highlighting the shift towards industrially processed foods. Concerns about UPF. While the author acknowledges concerns about consuming large amounts of synthetic molecules, they argue that most anxiety about additives is misplaced. The main issue is not the individual additives themselves, but their association with ultra-processed foods, UPF. Additives serve as a marker for UPF, which is linked to various health problems. The third age of eating. The author defines the consumption of UPF as the third age of eating, emphasizing its recent emergence in human history. This age represents a significant departure from our evolutionary past, where food was primarily consumed in its natural or minimally processed state. Humans' evolving relationship with food. Even when eating natural foods, modern humans are more nutritionally aware than our ancestors, turning eating into an intellectual act rather than a purely instinctive one. The question of instinctive eating. Can humans, like other animals, rely on instinct to guide their food choices and maintain a balanced diet? Clara Davis's groundbreaking experiment, 1928. Davis, a Chicago pediatrician, challenged the prevailing authoritarian approach to child feeding. She was concerned about the rise of processed foods and believed children had an innate ability to self-regulate their diets. Davis conducted a long-term study where infants were allowed to choose their own food from a selection of whole, unprocessed options. The infants thrived, meeting their nutritional needs without guidance, and experienced no feeding-related problems. Earl, one of the infants with rickets, instinctively consumed cod liver oil, a source of vitamin D, until his condition healed, then stopped. The infants displayed food jags, focusing on specific foods for a period, which Davis believed reflected their internal regulatory mechanisms. Davis's experiment suggests humans possess an innate system for regulating nutritional intake. Children, when offered a variety of whole foods, can instinctively select what they need to maintain health. Food jags may be a natural part of this self-regulation process. While adults play a role in teaching safe food choices, children should be allowed to develop their internal guidance system. The appetite center hypothesis. Davis proposed the existence of a physiological mechanism that governs appetite and guides food choices based on the body's needs. A missing piece in medical education. The author highlights the lack of attention given to this innate nutritional wisdom in medical training. 6. How our bodies really manage calories. Precise calorie management. Our bodies have a highly evolved system for regulating calorie intake and body fat, honed over millions of years. This system ensures we consume the right amount of energy and essential nutrients. Natural body fat. Humans naturally have a higher body fat percentage than most land mammals. This is normal and not necessarily indicative of poor health. Obesity throughout history. While obesity has existed throughout history, it was extremely rare, before the advent of ultra-processed foods, UPF. The recent rapid increase in obesity, especially in children, is directly linked to UPF. Internal weight regulation. Our bodies regulate weight internally, similar to how they regulate water balance or breathing. This regulation is largely unconscious and influenced by hormones like leptin. The role of leptin, a hormone produced in fat tissue, signals the brain about the body's fat stores. High leptin levels indicate sufficient fat reserves, reducing the drive to eat. Short-term and long-term control. Our bodies have both short-term and long-term systems for regulating food intake. These systems involve complex communication between the brain and various organs, including the liver, pancreas, and gut. Pleasure and regulation. The hedonic system, responsible for pleasure and reward, is intertwined with the systems regulating food intake. While these systems were once thought to be in competition, they are now understood to be interconnected. UPF disrupts regulation. UPF disrupts our evolved mechanisms for regulating weight. These foods override our natural satiety signals, leading to increased calorie consumption and weight gain. Energy balance model. Scientists are developing a comprehensive model of energy balance that considers the complex interplay of hedonic and homeostatic factors in regulating food intake. External cues. External cues like advertising, packaging, and smells also influence our eating behavior, often subconsciously. Beyond eat less, move more. Simple advice like eat less, move more is ineffective for sustained weight loss because it ignores the complex and largely unconscious systems that regulate our eating behavior. UPF and obesity. The author concludes that UPF is the primary driver of the current obesity epidemic, although other factors like sugar consumption and sedentary lifestyles may also contribute. 7. Why it isn't about sugar. Sugar is not the primary cause of weight gain. While excessive sugar consumption can contribute to weight gain, it's not solely due to its effect on insulin levels, as previously theorized by Gary Taubes. Taubes' carbohydrate insulin hypothesis has been largely disproven. Rigorous studies, including those by Kevin Hall, have shown that calories from sugar and fat have similar effects on metabolism and weight gain when overall calorie intake is controlled. Low-carb diets can be effective for weight loss but are difficult to maintain. While some people find success with low-carb diets like keto, they often struggle to stick to them long-term due to the restrictive nature and cravings for carbohydrate-rich foods. Sugar's main harm is through tooth decay and increased appetite. Sugar, especially in combination with acids found in fizzy drinks and processed foods, significantly contributes to tooth decay. Additionally, sugar increases appetite, leading to overconsumption of calories. Ultra-processed foods, UPF, are the primary culprit in the dental crisis. The high sugar content and constant consumption of UPF, marketed as treats and snacks, are the main drivers of tooth decay in children and adults. Sugar as a sign of health in the context of UPF. In Carlos Montero's research, sugar was seen as a marker of health because it indicated home cooking. However, this doesn't mean sugar itself is healthy. It simply highlights how pervasive and harmful UPF has become. Call for warning labels on sugary drinks. The author advocates for mandatory warning labels on sugar-sweetened beverages and other UPF products with high sugar content to highlight the risks of tooth decay and other health problems. 8. Or about exercise misconception of inactivity. Many believe the obesity epidemic is due to a lack of exercise, but this is a misconception perpetuated even within the medical community. Conflicting research, numerous studies, often funded by Coca-Cola, downplay the role of calorie intake and emphasize inactivity as the primary driver of weight gain. These studies often feature the same authors like Stephen Blair, Peter Kaczmarzyk, and James Hill. The Fat Lie, an influential article by Christopher Snowdon, funded by a think tank with ties to the sugar industry, claim calorie consumption has been falling in the UK for decades, blaming weight gain solely on inactivity. Flawed data. Snowdon's argument relied on survey data that underestimated calorie intake. Doubly labeled water studies, a more accurate method for measuring energy expenditure, showed that people underreport their calorie consumption by over 30%. Energy expenditure is constant. Research by Herman Pontzer shows that energy expenditure remains relatively constant regardless of activity level. Our bodies compensate for increased physical activity by reducing energy used in other areas. Implications of constant energy expenditure. This means we can't outrun a bad diet. Exercise is still important for overall health, but it doesn't significantly contribute to weight loss. Coca-Cola's influence. Coca-Cola has funded extensive research and public health programs promoting the message that inactivity is the main cause of obesity, downplaying the role of sugary drinks. Conflicts of interest. Many researchers funded by Coca-Cola failed to disclose these conflicts of interest in their publications. Even when disclosed, the funding still likely biased the research findings. Misleading the public. Coca-Cola's strategy has been to flood the scientific literature and public discourse with misleading information, creating confusion and hindering efforts to address the obesity epidemic. 9. Or about willpower. Willpower is a misconception. The idea that weight gain is caused by a lack of willpower is pervasive but incorrect. It's similar to believing you can consciously control your oxygen intake. Obesity is primarily genetic and environmental. Genetic. Almost everyone with obesity has genes that predispose them to it. These genes influence eating behaviors like food choices and eating speed. Environmental. Food environments play a crucial role. These include the availability of healthy food, exposure to junk food marketing, and socioeconomic factors. Food swamps are dangerous. Areas saturated with fast food outlets and junk food advertising, food swamps, contribute significantly to obesity, especially among children. Junk food advertising is effective. Marketing for ultra-processed foods, UPF, increases consumption of unhealthy foods and decreases consumption of fruits and vegetables, especially in children. Poverty exacerbates genetic predisposition. People with genetic risks for obesity are more likely to gain weight in low-income households due to the prevalence of UPF and stress. Stress eating is genetic. While it seems like a conscious choice, the tendency to eat in response to stress is also influenced by genes. Willpower is not the answer. Blaming weight gain on lack of willpower prevents us from seeking real solutions like regulation, food pricing, and addressing poverty. The marshmallow test is flawed. This classic willpower experiment is actually more indicative of socioeconomic background than self-control. Personal experience is not universal. People have different genetic predispositions to weight gain. Some people are naturally less motivated by food, while others are more susceptible to food cues and environmental influences. Stigma and shame are harmful. Constantly judging people for their weight leads to internalized shame and can worsen the problem. Focus on support, not blame. Instead of nagging loved ones about their weight, focus on understanding and supporting their individual needs. Addiction may be a key factor. UPF may be addictive, and treating it as such could help people escape its influence. This point is presented as a potential area for further exploration. 10. How UPF hacks our brains. Week 2. Enjoying frozen meals like the Morrison's all-day breakfast, 768 calories. Reminded of childhood airplane food, specifically Air Canada's 1986 macaroni and cheese. Learned about the history of frozen meals. Originated as airline food, Stratoplates. Swanson's TV dinners popularized them in the 1950s. UK now leads Europe in ready meal consumption, £3.9 billion market in 2019. Compared the ease of a ready meal to cooking a fresh meal from scratch. First exposure to an ingredients list full of unfamiliar additives, diphosphates, flavorings, etc. Week 3. Started working on a study about the effects of UPF. Began learning about the potential harms of UPF from experts. Nicole Avena. UPF can be addictive, activating the brain's reward system like drugs. UPF may be engineered to be hyperpalatable, triggering cravings. The base ingredients of UPF might be unpalatable without additives. Started noticing the lack of real food in UPF, especially snacks and cereals. Example: Grenade Carb Kilobar, made from modified carbs, protein isolates, and palm fat, with added flavors and sweeteners. Fernanda Rauber, UPF is not food, but an industrially produced edible substance. Packaging, preservatives, emulsifiers, and lack of fiber can harm health. Example: Turkey Twizzlers with 37 ingredients and only 63% turkey meat. Week 4. Physical effects of the diet became noticeable. Weight gain, constipation, piles, anal fissure. Sleep disturbances and anxiety increased. Developed a negative association with UPF, seeing it as uncanny and unsatisfying. Family also started eating more UPF and experiencing its effects. Obsessively checking ingredients lists and questioning what constitutes UPF. Discuss the classification of baked beans as UPF with B. Wilson and Carlos Montero. The author's journey of increasing awareness and discomfort with UPF highlights the potential addictive nature, health risks, and lack of real food in UPF. Explores the impact of UPF on both physical and mental well-being. Raises questions about what constitutes food and the pervasiveness of UPF in modern diets. Ultra-processed foods, UPF, are often dismissed by industry using misleading tactics. They find common foods with minimal processing that technically qualify as UPF to discredit the entire concept. The NOVA classification system, which categorizes food based on processing level, has limitations. While useful for analyzing dietary patterns, it's not perfect for evaluating individual foods. Some foods, like certain varieties of baked beans, may be classified as UPF due to minor ingredients, but still be part of a healthy diet. The author's experiment with a UPF diet led to significant negative health consequences. Weight gain, hormonal imbalances, increased inflammation, and altered brain connectivity were observed. Brain changes observed in the experiment suggest a conflict between conscious awareness of UPF's harm and subconscious desire for it. Increased connectivity in areas related to food intake control, desire, and reward indicate this internal struggle. Even without harmful additives, UPF can still be problematic. These foods are often designed to promote overconsumption through their formulation and marketing, even if they lack specific harmful additives. The author's experience highlights the importance of considering the overall dietary pattern, not just individual foods. While some UPF may seem benign, a diet primarily based on them can have detrimental effects. The line between processed and ultra-processed can be blurry. Products like pre-made lasagna can be difficult to classify, as they may contain many common ingredients, but still undergo significant processing. Additives in UPF, while sometimes harmless, can signal other potentially harmful properties. Their presence often indicates that a product has been developed in a way that encourages overconsumption. The author's MRI results show that UPF can affect the brain's physiology. Changes in connectivity and neurotransmitter activity were observed, suggesting that UPF can impact brain function even in the short term. These physiological changes can lead to structural changes in the brain over time. Repeated exposure to UPF can reinforce pathways related to habit and reward, making it harder to resist these foods. Impact of UPF on children and teenagers raises serious concerns about the long-term effects of UPF consumption on developing brains. Potential negative impact on IQ and social performance due to interference with reward pathways. Need for further research to understand the consequences fully. Quitting UPF and brain rewiring. Optimism about the possibility of reversing negative brain changes by quitting UPF. Potential for improved concentration, memory, and overall well-being through healthy eating. Author's personal experience with UPF. Author successfully quit UPF cold turkey after the brain scan and diet. Experienced immediate improvements in sleep, bowel function, and work performance. Foods previously consumed compulsively became unappealing. Food addiction and UPF. Traditional concept of food addiction is scientifically controversial. Challenges in identifying specific addictive components in food. Author argues for recognizing UPF as a distinct category of addictive edible substances. Evidence supporting UPF as addictive. UPF consistently associated with higher scores on food addiction scales. High prevalence of problematic UPF consumption compared to many addictive drugs. Shared biological properties between UPF and drugs of abuse. Rapid reward delivery. Similar risk factors for drug addiction and food addiction, family history, trauma, depression. Comparable addiction symptoms reported for UPF and other addictive substances. Neuroimaging reveals similar patterns of dysfunction in reward pathways. Benefits of considering UPF as addictive. Reduces stigma, guilt, and blame associated with obesity and overconsumption. Shifts focus to the industry's role in promoting harmful products. Provides a framework for regulating UPF similar to tobacco control measures. Offers a solution to the problem of abstinence by targeting UPF specifically. Next steps. Author's desire to understand the specific mechanisms of UPF's effects on the body. Encouraging his brother to experiment with reducing UPF consumption.